All right, so this is an introduction to rate laws and reaction orders. We've got a basic equation, A plus B is yielding some products, and the reaction looks possibly a little bit different than you've seen. There's two arrows, I'll explain what that means in a moment, and then we've got a data table down below that's showing what happens to the initial rate of the reaction as the concentration of A changes and as the concentration of B changes, and these two changes are happening independently of one another. So a few things. Why are we talking about initial rate of the reaction? What we mean by initial rate is the rate the moment the reaction begins. Why wouldn't we just take the rate in the middle of the reaction or the end of the reaction? Is it just easiest? It actually has something to do with this second arrow that I pointed out earlier. Most reactions have a forward direction where the reactants make the products, but they also have a reversible direction where the products go back to being the reactants. And this is most reactions. There's very few reactions that only exclusively go in one direction. So because there's a reverse direction, this reverse direction affects the rate of the reaction. As soon as products start to form, those products are going to begin to react in the reverse direction. And then the resulting rate that we see is not a rate of just A and B combining to make the products, and it's not just the rate of the products breaking apart back into A and B, it's the rate due to the combination of those two processes. So it's impossible to see if changing the concentration of A or B is affecting exclusively the rate of the forward reaction if we're taking the rate at any point during the experiment. However, when it's the initial rate, there's no products available. So any changes we make to the concentration of the reactants we know are having a direct effect on that rate. So some basic conclusions that we can draw from looking at this data table is that, as we increase the concentration of either A or B, the rate is increasing. And this is something we knew when we first started talking about reaction rates. But let's try to describe the rate of the reaction, how it's being affected by the concentrations mathematically. We use a rate law to describe what happens to the rate as we change the concentrations of the reactants. So let's develop that rate law. So when I look at the concentration of A, when I start at 1 molar and I go to 2 molars, I am increasing the concentration of A by a factor of 2. And the resulting change that happens to the rate is it goes from 0.01 to 0.02. So my rate is also increasing by a factor of 2. So that's an interesting pattern there, but let's see if it holds when we're talking about the next change. When I go from 1 molar to 3 molar, what happens to my rate? Well, my rate goes from 0.01 to 0.03, so increasing my concentration of A by a factor of 3 increases my rate by a factor of 3. So if we wanted to describe how is the rate being affected, we'd have to look at what's happening exponentially to these changes. What I mean by that is A is being changed by a factor of 2 raised to some power x. And we need to figure out what power x is it being changed to by looking at what is the power that the rate is being changed by. So A is being changed by 2 to the first power, and this is equal to 2 to the first power here for our rate. So let's see if that exponent x holds even for the next change. What power does 3 have to be raised to produce this change in r? So 3, if it's raised to the first power, will produce the same change in r, 3 being raised to the first power. They're both being tripled. So my rate is directly proportional by my concentration of A raised to the first power. If I double A, R is going to experience the same change. It's going to be raised to the same power, 2 to the same power. If I triple A, R is going to be tripled as well because it's going to be raised to the power of 1. But let's see if that holds for B. So I'm going to do the same thing now, looking at B's concentration. So when B is at 1 molar and it goes to 2 molars, what happens to my initial rate? It goes from 0.01 to 0.04. So this is interesting. I increase my rate, or my concentration of B, by a factor of 2. I doubled it. And what happened to my rate is it increased, but instead of increasing by a factor of 2, it increased by a factor of 4. Now this is interesting because now you might be noticing my exponent cannot be 1 on this factor of change right here. I'll use Y to be a little bit different from B or from A. So what power does 2 have to be raised to get me a change of 4 in my rate? Well, if I square 2, that will get me 4. That'll get me my factor that I changed my rate by. So let's see if Y is 2 even when we're looking at the next change in concentration. So when I go from 1 molars to 2 or to 3 molars, what's happening to my rate? Well, it's going from 0.01 to 0.09. So when I increase my concentration of B by a factor of 3, my rate is increasing by a factor of 9. So once again, it's not the same factor. So my exponent is most likely not going to be 1. So I got to figure out what is the exponent I'm raising this 3 to that will produce a change of 9 in my rate. So 3 to the Y, what does 3 have to be raised to get 9? Well, if I square 3, that'll get me 9. So once again, I'm seeing that I'm having to square the factor I changed my concentration of B by to get the rate, or the factor I'll change my rate by. So my relationship between the rate and the concentration of B is going to look a little bit different. The rate is directly proportional to my concentration of B squared. This is what my relationship is, because any factor I change B by, R is going to change by the same factor but squared. So how do we reconcile these two different equations? How do we create one good old-fashioned rate law? Well, I can rewrite these equations as a more familiar equation. Directly proportional means that your two variables are changing by a constant of variation that we call K, right? This is mathematically how a mathematician would explain this. So I could rewrite these equations as such. Now they look a lot more similar because they have that constant of variation in common, and it is the same constant of variation. So if I wanted to create one rate law, I would just take these two equations and combine them. So my rate of my reaction is going to equal my constant of variation times the concentration of A raised to the first power times the concentration of B raised to the second power. So what do all of these variables mean if I were to start using proper vocabulary to describe everything? I want to do a color, I haven't done blue. R is specifically referring to the initial rate of the reaction. Initial rate. Remember, we can't refer to any of the rates during or towards the end of the reaction because they're affected by the reverse reaction. K, a mathematician would call a constant of variation. In this case, our chemists call it a rate constant, but it still serves the same function. It's a constant of variation. We just call it a rate constant. The A in brackets is the concentration of A. What I want to make a note of is this exponent right here. What does that exponent of 1 mean? This exponent of 1 describes the order of my reaction in regards to A. This reaction for A is a first order. So this is first order in A. So my exponent of 2 on B's concentration means that it's second order in B. So that's two different orders. So if we wanted to just describe the overall order of the reaction, the overall order is going to be the sum of the orders between A and B. So the sum of order 1 and order 2 will get us an overall order of 3. So this is how we would get a rate law and how we would get the order of an overall reaction by looking at experimental data. So you'll see probably a common notation for like a general equation for a rate law written as such. The rate of a reaction is equal to the rate constant times the concentration of your first reactant raised to some power times the concentration of your second reactant raised to some power. Now, here's an important point that I'm going to make. Students commonly confuse this. X and Y, these exponents, must be determined experimentally. They are not going to be the same as the coefficients. Sometimes they might be, but many times they will not be the same as these coefficients A and B right here. So we must look at experimental data to figure out what are these orders. So must be determined experimentally. They can't be determined simply by looking at the reaction. As convenient as that would be, it's just not the way that first order and second order works. So let's look at some examples of real life rate laws. We've got 3 reactions right here, and the point I'm trying to show you is examples where the coefficient is not the same as the exponent. So right here, this is a first order reaction. It's got an exponent of 1, yet my coefficient for this reactant is 2. It's not the same. That's okay. However, I've got an example right here where both hydrogen and iodide are first order reactions, and they also have coefficients of 1. That's just one example where they happen to be the same, but it doesn't mean that it's the cause of those reactants being first order. My last example is probably my favorite because I have one reactant that is first order, which makes, kind of a tricky, relationship here because the coefficient is 1. However, they're not related. But the example that really drives that home is, look, I can have a half order. I can have a half order reaction despite my coefficient not being 1/2, despite none of my coefficients being 1/2, and that's okay. You may find that you have exponents that are fractions, and there would be no way that you'd have a coefficient that could ever be a fraction. So the point I'm really trying to drive home here is that X and Y in this equation have to be determined by looking at a data table much like what we have here and seeing how do these two variables vary in regards to one another. So hopefully this was